I'm going to talk about space particle dualism theory. It's an approach to quantum gravity which I started developing in 2005. And it's based on an interpretation of quantum theory, which I'm going to explain here. So the curious thing about quantum theory is that it's very intuitive. At first, when you want to measure something, you would have to disturb it. So when you use small wavelength, you're hitting it a lot, so you know the position, but you don't know the impulse. But the surprising thing is that at the same time, this is not just a limitation to our knowledge. At the same time, it's a limitation to nature itself, which is suggesting idealism, that that the world we observe is actually a part of us. Because if the limits of what we can know are at the same time the limits of nature, that suggests that nature is an extension of human consciousness. So that's shown in the double slit experiment. There you can see that the wave function representing our knowledge about nature is at the same time it's interacting like a physical object, but it's just information. Then you can have different interpretations of quantum mechanics, like the many worlds interpretation. So what is measurement? The orthodox interpretation says that a measurement caused the collapse of the wave function. But what defines a measurement? Well, the world is made of information. Information requires somebody to know it. Measuring is about knowing, so measurement requires consciousness. What about other interpretation? Many worlds, many minds, the coherence theory? Well, no, because of Kurt Gödel proved that our ability to think is not an algorithmic process. So our brain cannot be a machine. If our brain is not a machine, there must be some free will involved in human thinking. And that's really only makes sense if you adhere to the orthodox interpretation, which just has one world and us choosing among different alternatives. You could try to make such a thing in a many worlds theory where you choose your path through many worlds, but it's a messy thing. It doesn't really work. And I argue that way in my book too, in chapter 2. So what about quantum strangeness, quantum non-locality, entanglement, superpositions? How do we explain these? We have to interpret them in a certain way. How can a particle manage to be at many places at the same time? Well, to answer that question, we have to look at phase space. Phase space has, for every particle, has 6 dimensions, 3 for position and 3 for the impulse. Now, a nice thing we can do here is, first we can represent the passage of time by a moving point of consciousness in phase space. One position here representing one state of the universe. Similar states are close to each other in this phase space. Now, but this is a very classical picture because one point is just one classical state. So we can make it quantum mechanical by extending this point of consciousness into a cloud of consciousness. This corresponds to an equivalence group of space-times. So all these spaces are indistinguishable for the conscious observer. So the wave function collapses every time the eye of the observer is reached and the conscious level is reached. So it takes probably 0.35 seconds for the wave function to collapse every time. But it's important to note that that the equivalence group is defined on the past light count only. So here we can have everything vastly different. And actually, I don't suggest that we should take this as being real. I suggest that we just assume that the past light count is real, and that's all there is of reality right now. So this is the similar worlds theory, or better, similar worlds interpretation. It doesn't work as an independent theory. It's part of space particularism, which we will come to shortly. So a nice property of this theory is that you have each quantum state is a state of a whole space, or a space-time if you want. So in each of these similar worlds you have spins being orthogonal, and so you don't need to wonder that if you measure and pick out one possibility that you find orthogonal spins. There's no need for a spooky action at a distance. Everything is explained by this structure. So, but then we have a problem. We have a relativity of simultaneity. So that's kind of a problem at first sight, because in this phase space picture we had one point representing the universe at one moment in time, but that's kind of ignoring relativity, right? So in relativity theory there are different planes of simultaneity, and this seems to be a problem. And it's not really only applying to high speeds. If you had an alien very far away walking into our direction, it would bring our future onto his plane of simultaneity, and if he walked away from us slowly, it would bring our past into his plane of simultaneity. But then we have to think about, can he see our future? Can he collapse our future wave function? No, he cannot. So therefore, I think we don't need to assume that the whole of space-time exists. I also want to stress that in quantum mechanics, the wave function collapses everywhere simultaneously over space. So that's very different from relativity theory, and it suggests that there is actually a preferred frame of reference, which is, in my opinion, created by entanglement. Yeah, so the past light cones is everything that exists of space-time. I don't believe in a four-dimensional space-time where we are sort of sculptures in an unchanging continuum. So the passage of time looks like this. Every sheet here represents all the similar worlds, and the group of similar worlds is different in every moment. So when you make a measurement, you rule out certain worlds, so they disappear from the equivalence group. So there is what I call Eigenwegener's conflict. He gave a speech about that in German. German was not his native language. It was quite interesting. The reason why Eugen Wegener gave up on his own interpretation of quantum mechanics is that he was troubled by the way he believed that conscience caused the collapse of the wave function, but he was troubled by the way how if I observe you, you're on my past light cone, and when you observe me, I'm on your past light cone, and this kind of forces, this is the danger is that this leads to solipsism, that I say, okay, I only measure you how you were in the past, so you don't exist in the present. And it's very hard to figure out how to do quantum mechanics in a space-time with light cones. So I believe that the solution to that is entanglement. So when we are entangled, everything here around us is entangled because everything has had interactions in the past. So that way, the wave function can collapse simultaneously everywhere here. So, but we have no entanglement with the remote universe. So I believe that quantum mechanics leads to a form of solipsism, which can be prevented by quantum entanglement, but only here on Earth, not far away from it. Because only entanglement which was established after the emergence of consciousness counts. So This theory, the similar worlds theory, can explain why a particle can be on many places at the same time, but it does not explain why probabilities are wave-like. If you just apply similar worlds theory, you just get a simple mountain as the probability distribution. So why are probabilities wave-like? Then the wave nature can be understood as a movement in another complex dimension of space, which makes the particle undetectable on some of its superposition paths of movement for a moment. So I suppose that every particle carries its own quantum of space, which is complex valued. So, and the particle orbits this quantum of space, and it leaves the real part for a moment and then comes back again. So the result is that on every path of movement, the probability to measure the particle there goes up and down like a wave, and that happens on every single path. So on some paths it's likely to be measured, on others it's less likely. So the result is a wave distribution. Yeah, this leads over to space particularism, which I already just mentioned. So let's deduce space particularism. But according to Einstein, space can bend and twist. If so, it must be something, it can't be nothing. It must be made of something. If it can twist and turn, there must be some constituents of it. So there's a nice little idea which many people had. It's a pretty obvious idea to have. It's the black hole particle analogy. First of all, it's not correct, but it leads to the correct idea. It leads over to the correct idea. If particles are point-like, then there must be tiny black holes. An idea Sheldon once described to Hawking in an episode of Big Bang Theory. It was quite funny. The advantage is gravity shields itself away. In particle physics, there's a problem that if an electron is infinitely small, then it must have infinite energy, because to take an electric charge and press it into an infinitely small volume takes infinite amount of energy. But if you look at when the event horizon forms out, then basically the information about any further energy increase is trapped inside the horizon, so the energy doesn't go to infinity. Precondition is that radiation stops for black holes smaller than the Planck length, and you can easily calculate that that's the case. Other people have done that too with other methods. I was looking at when the energy of the radiated photons becomes higher than the whole mass energy of the black hole. Others use the Planck time, but that's not so important. Yet such small black holes couldn't eat anything. So the question is, can we use their event horizons as building blocks for space-time itself? That's the idea. And indeed, the surface of a black hole is the most direct way to link mass or energy to a surface. But the problem is that, first elaborate on the idea a bit. One could try to construct a three-dimensional space out of two-dimensional surfaces, seemingly straight paths of a particle in flat space. So it seems it goes straight, but when we zoom in on it, we find that it goes zigzag from one elementary space to the other. Are there enough of these elementary spaces to form a gapless pattern of space? So that was one of the big initial concerns. It was concerning me most in the early years. So the patchwork consists mainly of virtual particles. Obviously, if you have a particle here and a particle there, you cannot form a space from that. So, but you have all the particles of the quantum vacuum, yeah, then you can do it. But you need the elementary space to be bigger. They cannot be as small as an event horizon, because an event horizon for an electron, it would be 10 to the power of minus 57 meters. That's too small. Because when you quantize the vacuum, you have to have one fluctuation every Planck length. So you're doing some sort of second quantization. And when the elementary space is too small, you can't have them connected one to the other. So you need to introduce a new constant. You don't use G, you use GE. and that's basically a gravitational constant that is scaled up. It's scaled up so that gravity, it's like gravity becomes as strong as the electromagnetic force. Initially, I thought it should be the united GOT force, but then I realized that running of coupling would make that redundant. So actually, one has to use, because then you would have to use a different electron mass, you would have to use the naked electron mass, and the two effects would cancel out. So one just uses a G that's proportional to the, its strength is as strong as the electromagnetic force. So that's the formula for it. It's 10 to the power of 25 in some units.
Where is that? This equation, where is coming from?
It's basically, you get this equation from looking at the coupling constants of gravity and of electromagnetism, and then you get this equation.
Then you use the mass of electron, not of proton. Proton has to do it.
That's
Maybe it's a type should be depend on the mass of electrons, because this is the elementary particle. Proton
but no, gravity is, in my opinion, gravity is a side effect of the strong force, and electrons,
okay.
in my theory, electrons don't really have
so that
any.
that was missing.
Yeah.
Okay.
So electrons actually don't have any gravity according to my theory. They have some short-range gravity of 40 meters only, and it's basically unmeasurable. Okay, but
this statement is not, is it theoretical or?
there is some experimental evidence that that gravity is correlated to the strong force, but we should do more experiments in that area.
No, I asked about the statement you said about electron gravity, which is 4 meters only, you said?
40 meters.
40 meters?
That's basically because the virtual, but I haven't been there. Every particle has an elementary space, and its size is proportional to the energy of the particle, and that constant we just saw. So if the virtual particle has an elementary space which is smaller than the Planck length, then basically the gravity disappears. But for gluons, virtual gluons, one virtual gluon they're self-interacting, so they can reach further.
I'm sorry, but your explanation is really the mix-up.
Can you finish?
cannot understand it all.
Can you
Yeah,
finish?
because it's reaching forward.
Maybe
It's reaching
later.
forward.
Sorry.
We are not yet there. Okay, so there's I use the concept of granular or broken dimensionality. So the more connections you have from one elementary space to the other, the closer you get to here. You get to two-dimensionality. So these elementary spaces are one-dimensional. There's only one dimension, and through the connection, you get something two-dimensional. So when we so for 2 dimensions, you with 10 connections you reach 1.9, the dimensioning 1.9. And for 3 dimensions, you need 100 connections in order to get 2.9. That's why I asked, why I added the square root, because for 2 dimensions, it's fine to have just 10 directions to access, but for 3 dimensions, you would need to have more directions to access in order to get the feeling of 3-dimensionality. So that's how it approaches 3. And I use this as a measure of like the curvature measure. So my theory doesn't use curvature. There's no curved space, it's granular space. So it's all differences in the density of elementary spaces. So if I throw down something and it falls down, it's because there are more pathways leading downwards. So when there are many elementary spaces here and less here, particles will naturally be attracted to those areas of space with more elementary space because there are more pathways leading through that. So it's still geometrical like Einstein's theory, but it's not based on curved space. And let's go back to that picture artwork I draw before here. So you see, this is German, says Elementarräume, elementary spaces. And you see here, this looks two-dimensional, but when you take the magnifying glass, you see that it's made of one-dimensional circles. And so the particle is not going straight, but on the surface of the circles. And here it's more dense, so if it was to pass by, it would be attracted by that deep blue area. So the hierarchy problem, why is gravity so weak? I suggest that that I calculated how many connections are there from one elementary space to the other, and what's the granular dimensionality of the pure vacuum, like with nothing in it. And this number is the result, 2.999, and there are a lot of nines. There are 35 nines, and so every change, every difference in granular dimensionality from one place to another place can only appear on the 36th digit. So that's why gravity is 10 to the power of 36 times weaker than the other forces, than the electromagnetic force. So this also solves the flatness problem. If space is made of these two-dimensional spheres, they can give rise to emergent three-dimensional space, but it has no real curvature, and that's why the universe can only be flat geometrically. So we don't have this choice. We don't have this huge coincidence. In general relativity, the chance to get a flat universe, a geometrically flat universe, is just 1 in 10 to the power of 62. Funnily, in inflation theory, the universe expands in a fraction of a second, expands to a factor of 10 to the power of 60. 10 to the power of 60, 10 to the power of 62, it's pretty similar. So that's, I believe, inflation theory is really an ad hoc theory. It doesn't have much explanatory power. Also prevents the vacuum catastrophe. If you combine quantum theory with general relativity, you get the problem that the quantum vacuum should tear the universe apart in an instant. But in space particle dualism, gravity from different directions cancels out. So it's the same like in Newton's gravity theory. Newton explained why the universe is not collapsing due to gravity, and he said it's because gravity from different directions cancels out. And also you don't have a center in an infinite universe. So I believe that gravity has no influence whatsoever on the expansion of the universe. So here comes the idea of entropic expansion. So I believe that the universe is expanding in order to compensate the entropy increase in black holes. So the entropy of a black hole is proportional to the surface area, and that's the power of 2. So that's why the universe expands, accelerates its expansion. If you feed a black hole linearly, 1 donut a second, you naturally, the entropy is going to rise exponentially, and it's a beautiful power of 2 function. So, but the problem is you need to have expansion also before stellar black holes appear. And you have all these supermassive black holes, and it's quite obvious. It's quite obvious that it's quite obvious that those supermassive black holes could not have formed out of stellar black holes. So I propose that they formed of actual dark matter, and they formed of actual dark matter, and that has to do with. So let's look at entropic expansion for a moment. So you have a cosmic volume here, and there are many small black holes, and the entropy seems to be increasing in there, in every black hole, but because many black holes leave the box, that's why the entropy density of the universe is never changing. It stays the same all the time. And when you follow this backwards in time, you can look at how the black holes shrink backwards in time, and then you can deduce an initial temperature for the universe, which is 6,000 Kelvin only. It's a very low temperature, and it changes a lot, but also the age of the universe has changed. Come back to that later. So where does primordial dark matter come from? I call it primordial dark matter because I treat the dark matter we usually talk about as being just normal matter in a very old universe, just burned out stars and such. So the initial approach was to look at complex mass and look at different combinations of the complex factors and get different types of elementary spaces out of that, which are complex. That approach is not quite correct in my opinion now, so I changed it. So that was the initial scheme, and was quite asymmetric. We have one electron here and 3 positrons here. It's asymmetry coming from complex numbers is great, but this is a bit too much asymmetry. And we have too many degrees of freedom. But we have some nice properties here. We can represent bosons as by reducing the number of dimensions. So instead of 2 complex dimensions, just 1 complex dimension that can explain a lot of the properties. For example, the spin of a boson to be always orthogonal to the direction of movement. So that can be explained by having 1 dimension less. And the 3 generations we could explain by putting more than 1 particle in 1 elementary space.
5 minutes.
Okay. We can change this model and actually get all the particles by just looking at the symmetry groups of rotations of the different elementary spaces. And we get SU3 as an emergent symmetry group. So so we get 50%, we would get 50% dark matter here, initial dark matter. So here, the horizon problem is also solved because entropic expansion doesn't allow too big anisotropies. But then there are small differences, and those are interesting. There are 4 major cold spots, and they are in interesting positions. They're at the north and in the direction of the north and south pole of Earth, and in the north and south pole of the plane that's defined by the orbit of the Earth around the Sun. And that's indicating that it's actually true that all wave function collapse where conscious observers are. So, so it's aligned with the equinox and the ecliptic. Yeah. So, and then there are all these, also these non-Copernican patterns here. The distribution of galaxies. I initially thought that that's also evidence for the conscious collapse wave function hypothesis. And there is a little bit of that here. There's the north and south asymmetry. I had this, for a long time I was using the time it takes for the sun to go from one major spiral arm to the next to explain this pattern, how the universe can be built up from the present to the past. But I later figured out that using baryonic acoustic oscillations is sufficient, and that can also prove out my figure for the age of the universe. So basically the theory is saying that there are no aliens because we collapse the wave functions here, and solipsism can only be prevented to quantum entanglement. So it also prevents time travel because there are no wormholes in this scheme, and there's also an information paradox because black holes cannot evaporate away because gravity comes from charge. So basically you have a charge here and it emits virtual particles, virtual photons or virtual gluons, and then you have a higher density around that, and that's gravity. So the math of space particularism, there are the different equations here. We had this, and you can also look at when the elementary space becomes bigger than the wavelength, and that's where you can actually test it. And I believe that the particles we have in particle accelerators are already beyond that, and they already have structure, and we could actually be testing that. So here are the different equations. Impulse of dark matter. Dark matter needs to be cold, and so here's how I quantize the quantum vacuum, and here's charge gravity. So I'm not using G. I abolished G. So instead of mass 1 times mass 2, I have number of quarks 1 times number of quarks 2. And you can also write it like this. This is cardinal hypercharge. Basically, you count how many individual charges there is, because the usual hypercharge is just 0. You can have that also for electromagnetic force, but it's strange. So, and that's the very important formula. It's also on a T-shirt I printed. So this is Hubble at different times. So if time is 0, then this whole term becomes 0, and we have the initial Hubble value. And if t is t0, then these cancel out, and we have h0 minus h minimum plus this, so we are left with the present Hubble. And this is how it's defined. It's the minimal mass of dark matter black holes, which can be derived from my theory, and the average size of supermassive black holes, because I believe that all supermassive black holes came from primordial black holes, and that's
maybe go to the
okay. So the age of the universe, according to my theory, is 42 trillion years, and you can derive that by looking at the decoupling temperature. Yeah, and proved through dark matter percentage. This figure leads to a dark matter percentage of roughly 90%, and that's what we observe in the Milky Way. And then the full age of the universe, 86 trillion years. So that's because the initial temperature is 6,000, and we can derive that by looking at the entropy density of the universe. And for that, I had to calculate the entropy of all the supermassive black holes in the universe and the distance to Earth, because the distance derived from space particularism theory is different from the usual intergalactic distances, so the entropy density is smaller. So when you go through all those black holes, it took me quite a few days to finish this. So we arrive at this entropy density, and we can use this to calculate the initial temperature by squeezing down the black holes, and then you can equal that to the photon entropy. So, and then you can also check with speed of acoustic oscillations in the early universe. This is the speed. It's pretty low. It's not half the speed of light as you see in the Standard Model. It's because the temperature is so much lower than in the Standard Model. It's just 6,000 Kelvin. And then you also come up with the observed acoustic oscillation. Those are the circular patterns in the distribution of the galaxies. It matches quite well. Yeah, so these are the different constants. This is just a little review. So this is the most important here. You plug in the redshift and you get how the light travel distance. Yeah. So minimal distance, if you leave out the assumptions. Minimal black hole mass, dark matter black hole. And this is the space part of, this is initial temperature of the universe. You have that. Age of the universe.
Okay. Can you go to the conclusion, please?
Yeah, this is basically the conclusion. This is just a summary. Yeah, I haven't finished basically yet.
All right.
Yeah.
Thank you so much.
Yeah.
So I guess we are very late, so we turn to the break. There is a break, no? Isn't it?
No. Yeah, there's supposed to be a break at 4.
4:15. 4.
Yeah, at 4, but we're out of nowhere. Maybe we